Hey, Waf.
Hey, Kflan. Now let's nerd out with Bayes' rule that allows us to solve complicated problems that may be difficult or impossible to put in a contingency table. And it gives us a formula that if we can figure out every part of the formula, we'll always get the correct answer. So let's look at this first problem. So consider this following table of survival rates and life expectancy of a certain population at birth. So we have a number of different probabilities of people's survival rate at a given age. So at birth, if the probability of living to the age of 55 is 90%, 60 is 85%, 65 is 75%, and 70 is 65%. So we have different probabilities of how long you might live in a certain population at birth.
And it keeps going down as you get older.
And that makes sense because this is probability of life expectancy at birth. So you have to live to 65 to be able to live to 70.
Exactly.
So what's the probability of a 6-year-old reaching the age of 65? So this is not just the life expectancy of reaching the age of 65 because we know they've reached the age of 60. So we know they've already made it most of the way to 65. So that's going to be a higher probability than the probability of living to 65 at birth.
Right.
So let's write this in probability notation. So I want to know what's the probability of reaching 65 given that you are 60. So here we don't have this conditional probability. We don't know from this table what the probability of being 65 given you were 60. So what we need to do is we can apply Bayes' rule and reverse this and see if that helps us at all. So I'm going to say the probability of being 60 given you were 65 times the probability of, and then I'm just thinking PH given D is P of D given H times P of H over P of D. So our H is going to be 65 and our D is going to be 60. So I'm going to say it's going to be P of H. So our H is 65 divided by P of 60. So I simply wrote out Bayes' rule, applying it to this particular problem. So this is interesting. So what is the probability that you were 60 years old given that you were 65?
So I guess that has to be 100%, right? Because if you are 65, you know at one point you had to be 60.
Yeah, so one way to look at this is, what is the probability you had your 60th birthday given you're at your 65th birthday? And that is 100%, so that's just a 1. You're guaranteed to have had your 60th birthday if you've just turned 65.
Exactly.
So then that one's easy. So even though we're not given it explicitly, just by interpreting the problem, we're able to find out more about this. And then we just have to multiply the probability of you reaching 65 with no priors. So that's basically 65 at birth. So that is 0.75.
That's what we were given, right?
That's just given right here. And then probability of reaching 60 with no prior, so at birth, is 0.85. So Carly, do you have Python? Can you help me out with a calculation?
For sure. So I want to do...
So the probability of you turning 65, given you're 60, is equal to 0.75 divided by 0.85.
And Python gave me 0.8824.
8824. So that converting to a percentage is 88% probability that if you've turned 60, that you're going to have a 65th birthday if you're part of what's being modeled by this population. So this is higher. This 88% is higher than the 75%, which is exactly what we expect to see.
Yes.
And I always like to kind of double check this every time we see it. And because we had a formula, we were able to just plug things in and know that we were able to get an answer as long as we followed the formula.
That sounds great. Do you have any more?
Got one more puzzle for us. So this puzzle comes from a real research study here published at the University of Illinois. So this says the University of Illinois developed a saliva test that is convenient, repeatable, and large scale as a key weapon to help control the spread of COVID-19 pandemic. They released a paper in 2020 with data from the saliva test. During the time of this analysis, 9% of students had COVID. So I'm going to say probability of COVID was 9 out of 100. So I'm going to underline that since I've got it. 89% of people with COVID-19 will correctly test positive. So the probability of a positive result given you had COVID, or you have COVID, is equal to 89 over 100 for the U of I COVID test. And then, however, 1 people without COVID will also test positive. So the probability of a positive test result, given that you do not have COVID, is equal to 1 out of 100. And now this problem asks us, what is the probability that somebody actually has COVID given they received a positive test result? So we want to know the probability that they had COVID given a positive test result. So here, we don't actually have this given in our problem anywhere. We don't have probability of COVID given positive anywhere. We only have probability of positive given COVID. And because of that, we can definitely use Bayes' rule here because we have the inverse, which is an obvious suggestion of saying, hey, this screams Bayes' rule. So here we can go ahead and write this out. Again, remember Bayes' rule is P of H given D is equal to P of D given H times P of H over P of D. And so probability of COVID given positive is the probability of a positive test result given COVID times the probability of COVID divided by the probability of a positive test result. And now let's dive into the specifics of this problem. So the probability of positive given COVID is something we were given. That was 89 over 100. And then we want to multiply by the probability of COVID. So I think in the problem, 9 out of 100 students had COVID.
Exactly.
And then here we have the probability of positive. So what's the probability of just a positive test out of the whole population?
So it looks like we weren't given that specifically, but we were given all of the probabilities that we need to calculate that. So we have the probability of getting a positive test result given that you had COVID and given that you didn't. And then we know the probability that you had COVID and we can figure out the probability that you didn't.
Exactly. So the probability of the overall positive is equal to the probability of having a positive test given you had COVID times the probability of you having COVID plus the probability of a positive result given you didn't have COVID, making sure to ensure that we've looked at the entire sample space. We looked at all the people who got a positive result with COVID and all the people with a positive result without COVID. And then when we look at all the people with a positive result without COVID, we also need to multiply the probability that they're in that group, so the probability of not having COVID. And go ahead and filling this in, the probability of positive given COVID is going to be equal to 89 over 100. The probability of COVID is 9 over 100, plus the probability of positive given not COVID is 1 over 100. Probability of not COVID is going to be 1 minus the probability of COVID. So that's going to be 91 over 100. So I get, if I just simply multiply this across, I get, Carly, can you give me 89 times 9?
Yes, for sure. 89 times 9, and that is 801.
801. And then I'm going to plus 91 all over 100 squared. So that's going to be 892 over 100 squared. So I'm going to go ahead and move that up into this formula because this is the probability of a positive test result. So I'm just out of curiosity because these are a real test, real research paper. What is 892 divided by 10,000?
0.0892.
0.0892.
Yes.
So during the time of this research study, 8.92% of the test came back positive. So that was a test positivity rate. That we had a test positivity rate of around 9%, and that's in line with the historical data. So you can look at U of I and see that we had about a 9% positivity rate during the early parts of the pandemic when we were first developing this test. So if we plug in this probability of positivity up here, we have then 892 divided by 100 squared. So I'm going to go ahead and take this entire thing and unroll the division. So every time you divide, you multiply by the inverse. So we have 89 times 100 to take this first component. Second component times 9 by 100. And then the inverse of the division times 100 squared divided by 892. So the hundreds cancel out, 100 squareds cancel out. And now we have 89 times 9 over 892. So Carly, can you do this little math with Python, helping us out?
Yes, so 89 times 9 is 801.
801 over 892.
Over 892 is 0.89798.
89798. So that is 89.798%. And what's always helpful is we got this result, but what does this result mean? So let's see, what did we solve for? we solve for the probability of COVID given a positive test result. So if you had COVID and given that you got if you got a positive test result, so this is your given you had a positive test result, the probability of having COVID was right about 90%. So that means that if you got a positive test result from the University of Illinois saliva testing, you were about 90% certain that you actually had the COVID disease. So this is a really kind of strong result that you can be pretty sure that if you had this, that you got that positive test, you have pretty high confidence that you actually had COVID, which is very different than the Taylor Swift example that we looked at earlier in this series.
Exactly. And this was good because it's probably more problematic if you have COVID and don't know it, or didn't have COVID and think you did, than if you were related to Taylor Swift, if you got a false positive for being related to Taylor Swift.
And you're going to see that medical tests, as you look at approval agencies like the U of I got FDA approval based on part of this study because we had to demonstrate that the results were solid and that they were statistically sound.